Alright, I'm going to try to position the camera. I noticed I could probably have it more turned this way and get more board. Kind of looks tilted now, but is that enough? Yeah, okay, that's probably good. Alright, I'm just gonna give it a little second because it just turned 4 o'clock. But alright, yeah, I just wanted to take this time to go over a couple exercises. I figure Wednesdays I could do some exercises on the board, so it's not just me lecturing all the time, and you can actually get some more kind of down to earth problems, maybe some calculation type linear algebra where we're just solving linear equations. That could be next week maybe. Or we're just solving problems from Axler. Maybe some of the problems I wasn't able to get to during the lectures, or I think they're just kind of illustrative of some good linear algebra, either theorems or ideas or etc. Okay, hey Rex. I think, yeah, so we got I was asking for submissions on the Discord. So on Wednesdays, there's a section, it says Wednesday exercise submission or something. So yeah, you can submit exercises there. I can't guarantee I'll go over them, but if they're good questions, I'll definitely go over them. So the first one was a very good question. It was sent by Offendum. I think it's like addendum with 2 F's. I like the name. So yeah, one of the viewers in the Discord sent in this problem. This was the person's username. Just gonna turn the brightness up on my computer so I can see. Yeah, so the question was, and I think this is maybe a theorem in Axler. I think it's from the first chapter though, not the stuff we've been doing recently, but still I think it's good to go over this. Good for APFF. Let V be a vector space over F, some field. Let the 0 vector be the 0 vector. And let 0 in the field be 0. So if I write the line on top, it'll be the 0 vector. If I don't put the line on top, it'll be the element of the field, the 0 of the field, which are technically 2 different things, right? So then we want to show the following 3 statements. So first we want to show that 0 times any vector is the 0 vector. What's a scalar? Yeah, 0 is the scalar. Yeah, 0 is in the field. Yeah, so we can scale by different numbers, right? One of the numbers we can scale by is 0. So the first statement is saying if we scale a vector by 0, we get the 0 vector. So that's kind of interesting. If we scale by any scalar the 0 vector, we also get the 0 vector. So basically, there's no way to scale the 0 vector out of being 0. Like somehow you, multiply it by infinity or something. Maybe then you get out of the 0 vector, but infinity is not a scalar, so. The third one is that -1, so every field has a 1, and -1 is going to be the additive inverse of 1, and the theorem says that -1, the additive inverse of 1, if we scale a vector by that quantity, then we get the additive inverse of the vector, which is -v. So it's almost like we take all these things for granted. So it's almost sort of hard to even think about how to prove these, because it's like we basically almost take these as axioms to begin with, right? Like, how could 0 times something not be 0, right? How could something times the 0 vector not be 0? Like, how could -1 times v not be the negative of the vector, right? So it feels like these things should just be axioms or should just be true, but actually you can prove these from the vector space axioms, like distributive property, associativity of the scaling. So we have all these axioms that say we have an abstract vector space if these things are satisfied. And so these things should follow from those. We just have to figure out which rules which rules imply 1, which rules imply 2, which rules imply 3. True. It's a hallucination. Was that good, Rex? True. True. Okay. Oh, I forgot my eraser over here. Okay, so this is the problem. Pause the video if you still need to think about what these statements mean. But yeah, let's show that they're true. Okay, so for 1, let's just rewrite the statement. So 0 scaling any vector is the 0 vector. All right, so you can see in my notes I actually started to solve this and then I figured out I was doing it completely not the correct way. The easiest way here is, so the idea is that we're trying to show that this is 0. One way to show that something in a group is 0, right? Because this is a vector, so it's a vector in an abelian group. So one way to show something in a group is 0 is to show that when I add it to something, it doesn't change that thing. And so this, how can we do that here? Well, we can use the distributive property, so I can rewrite 0 as 0 plus 0. Right, because in a field, if you add 0 to any element, you get itself. So in particular, it still works with 0. So 0 plus 0 is 0. Since I put parentheses, this is literally just the same thing, because 0 plus 0 is 0. Then I can use distributive property. To distribute the two zeros, so I get 0 times 0 times v. Putting random arrows here for no reason. So 0 times v plus 0 times v is equal to 0 times v. Right, and that's what I was just saying. So we have an element plus itself is equal to 0. Well, now I can use left cancellation, or it's an abelian group, so left cancellation is the same thing as right cancellation. But I can cancel one of these terms with this, and I should get 0, right? So I can, or you can think of this as, this is plus the 0 vector, right? So we have something plus itself equals that same thing plus the 0 vector. Now I can cancel these terms on the left. That's left cancellation in a group. If you go way back to the maybe lesson 1, literally, I think lesson 1 I talk about left cancellation in a group or right cancellation. So this is left cancellation. We have something plus something equals something plus the 0 vector. I can cancel, these two are the same thing. I can cancel them. So then we get 0 times v is just equal to the 0 vector, because the other two go away. And that's what we wanted to show. Hey, Kyler. Kyler? Is that how you pronounce it? I know that's probably not your actual name, but. Okay, so that's the first statement. We showed that scale any vector by 0, you get the zero vector. Use distributive property, left cancellation, get the 0 vector. Oh, offendum, we're doing your problem. Yeah, so this was the first part if you're just getting here. This was the first proof. So we showed 0 times any vector is the 0 vector. Okay, so the second part of the problem says to prove that any scalar times the 0 vector is the 0 vector. Oh, wrong page. Oh, this one looks pretty easy. Right. So now we're just going to use the distributive property. It's very similar, but we're going to use the distribution for the vectors instead of the scalars. So we're going to prove this. So C times 0. Of course, C is any scalar. I hope I don't need to write that. All right, C is in F. Let C be in F. It's a scalar, arbitrary scalar. This is equal to 0 vector plus itself, similar to the last proof. I'm putting a star here. This is like the scalar multiplication, right? Sometimes we don't even put anything there. So when you add the additive inverse, it's the same as cancellation. Yeah, because that's actually how you prove cancellation. Yeah, you add the additive inverse and then you use associativity to say that you can just get rid of the term. Because, yeah, once you associate any element in a group with its inverse, the product is the identity, right? And then when you multiply by the identity, it's like you're not doing anything, so you can sort of just get rid of the term. That's how you prove the left cancellation rule. Yeah. Okay, so very similar to the last one, except now we're using distributive property on the vectors instead of distributive property for the scalars. And we're writing the 0 vector as the 0 vector plus itself instead of before we had the 0 in the field plus itself. So very, very almost identical proof, but it is technically different. So now distributive property says this is C times 0 plus C times 0 vector. Or sorry, equals, there should be an equals here. Very nice to have you here, Kyler. Right. And now it's same argument. So we have something equals something plus itself. The only way that's true is if that something is 0. So basically you can, plus 0 again here. Cancel. We'll do right cancellation this time just because we're fancy. And then so the 0 vector equals C times 0. And that's what we wanted to show. Okay, so basically before we used, I said distributive property, but I guess you need to be a little careful about, there's 2 different distributive properties. So the first one used distributive of the scalars, scalar addition. This is using distribution of the vector addition. Okay, any questions? I think these proofs they're nice to go over, but they're pretty straightforward once you see them. I think the hard part is like sort of coming up with like which axiom you're supposed to use, but and actually I kind of got confused myself when I started doing it earlier. I had to like just erase my work. I was like, this doesn't seem right, and then I found the correct way obviously right after. Okay, and then the last one we want to show that if I multiply by a scalar of -1 a vector, then I get the additive inverse of that vector, or sometimes we'll write it as negative v. So that's the last one, number 3. Okay, so last one we want to show -1 times a vector is the additive inverse of the vector. And I believe, what is this? Yeah, this one also uses distributive property of on the scalar side. But this time, instead of trying to show something's equal to 0, we're going to show that this plus this is equal to 0. So slightly different here. Right. So what we start out with is we know from part 1 that 0 times v is the 0 vector. And then what we can do is rewrite 0 as 1 plus -1. So 1 plus its additive inverse should be 0. And the intuition here is that we're adding the inverse of -1 here because we want to use the distributive property and figure out what is -1 times v. Right, so we kind of artificially created a -1 right here by adding 1 plus -1 is equal to 0. So now we have a -1v once we use the distributive property. So that means that this, by the distributive property, again for scalars, this is 1 times v plus -1 times v, and this equals the 0 vector by part 1, because 0 times anything is 0. Then now we're going to use one of the axioms that says 1 times the vector is we just get the vector back when we scale by 1. So this is just saying that, the vector plus -1 times the vector is 0, and that implies that these are additive inverses of each other, because when I add one to the other, I get 0. So this is -v. All right. Or really, I guess we could just stop here and say it's, inverses are unique. So if this plus this is 0, well, this is the unique additive inverse of that. Formal or informal proof, which path shall we go down? Are you talking about for this problem, Rex? Or what do you mean? Okay. Unless Rex tells me what he's talking about, I'm gonna go on. So that was the problem from one of the viewers in the Discord. And actually, I was planning on going over this problem probably earlier. I just didn't fit it into one of the lectures, so I'm really glad somebody asked this problem. So formal or informal, which path shall we go down, like proofs we do in this book? Do we go down to the axiom level every time? No, that's what I was saying. Like, these seem obvious. They almost seem like axioms themselves. So that's sort of like there's almost nothing below them. So for this you have to go to the axioms because they're such basic statements. They're almost a lot of other statements in linear algebra follow from these. So you kind of have to start from the axioms. You prove these simple statements first, and then of course you can prove more complicated theorems, and a lot of them may in some way or shape or form depend on these in some way. So yeah, usually, math, actually we try to avoid going from the axioms, right? The whole point of math is we want to start with reasonable axioms and then develop theorems which, are sort of more developed, so we don't have to go back to the axioms every time. But of course, these are just very basic statements, so there's they kind of need to be proved from the axioms, because you're not assuming anything about the vector space tangibly. It's just some arbitrary vector space. All you know is that it satisfies the axioms. That's it. Yeah. So you want to prove theorems. I mean, that's why you never want to go straight from the axioms. You want to prove theorems. It just happens that these statements are very, very basic and simple. Basic in a like foundational way, not like basic like we can just skip over them and not think about them, but they're basic in the sense that they're like one step from the axioms. You have the axioms, and then, I mean, you saw the first two. We just basically said distributive property, one line, and then we got the next statement. So it was basically like a direct consequence of the distributive property. Okay. So I picked a couple other exercises because I only saw the one we just did in the Discord, but I picked a couple others that I thought were very interesting to go over. First one is 2A. So this is section 2A in Sheldon Axler's book, Linear Algebra Done Right. And this is problem 7, part A. So show that the list 1 plus I, comma 1 minus I, so two complex numbers, is independent viewing the complex numbers C as an R vector space. Okay, so essentially what the problem is saying is you have the complex numbers, so that's all like set of all A plus BI, where A and B are real numbers. Right, and the set of all complex numbers actually forms a vector space over the real numbers, because you can take any complex number and you can scale it up or down by a real number and you get another complex number. So what this is saying is that you have this list of two vectors. We want to show that it's linearly independent, but we're only allowed to take linear combinations with coefficients in the real numbers, which is actually important here. And in part B, we have to show that when we view these as complex vector spaces, where C, now complex numbers are viewed as a complex vector space, then this list is no longer linearly independent. So I don't want to rewrite everything. Basically, it's the same list, but for part B, you want to show that it's dependent. Show dependent list as C vectors. So if we take this list and now we view them as complex vectors where the scalars are allowed to scale by complex numbers, then this list is no longer dependent because the second number is actually a scalar multiple of the first number. Can anybody tell me what scalar multiple is the second number of the first number? So something times 1 plus I equals 1 minus I. What is the something? Close. Very close. No, it's not I. If I multiply by I, then I'm going to get I minus 1, right? Yeah, negative I, yeah, exactly. Is that an I? I can't even see from here. Yeah, so if I take this 1 plus I multiply by negative I get 1 minus I. So you can see that it's kind of hard to visualize because these complex numbers are two-dimensional. So a one-dimensional complex space is actually two-dimensional as a manifold, if you want to think of it like that. And a two-dimensional complex vector space is actually four-dimensional as a topological space. So yeah, this is actually kind of confusing here, but the fact is that the complex numbers are actually only one-dimensional over themselves. So if I have any list of two numbers, it automatically has to be linearly dependent, because the second number is always going to be a multiple of the first number. I can just, I can actually just divide out this number to make it 1 and then multiply by that number. And then that fraction is the ratio of the two, right? So in this case, if you did out that math, you would see that this number is negative I times the first number, and therefore it's a dependent list because the second vector is in the span of the first vector. Or in other words, you can just show that there's some non-trivial linear combination where this plus some multiple of this gives you 0, because all I have to do is multiply by. Oh, you said I, Rex, because, oh, right. I think, Rex, you were giving the answer for this plus I times this equals 0, right? That's what I think what you were saying. So I is the scalar multiple of this that you need to add to this to get 0. Yeah, so in that sense, yeah, you were correct. Okay, so I guess we can quickly show these two things. So let's just show it's independent if the coefficients are real numbers. So a1 times the first number plus a2 times the second number equals 0 implies that a1 and a2 are both 0 if they're real numbers, but doesn't imply they're both 0 if they're complex numbers. So that's basically a rewording of what we're trying to do. Okay, so I'll just quickly, or maybe not too quickly, but go through this again. Let's just write out the solution. Okay, so to show it's linearly independent, we want to take a1 and a2 to be arbitrary real numbers. And then we want to take a linear combination of those vectors. So it was a1 times, what was it, 1 plus I. One minus I equals 0. So here it's, you're obviously going to see when we do out the proof, but here it's going to, showing that these are linearly independent is going to depend on these being real numbers. So let's try to see where that shows up. So if I use the distributive property, right, this is just a1 plus a1i plus a2 minus a2i equals 0. So that means now I'm going to pull all the real and imaginary parts together. So a1 plus a2 is the real part, plus a1 minus a2 times I is the imaginary part. And so now you see that the only way this is 0 is if a1 and a2 are both 0, because you have, wait, why is that true? So we're trying to show that a1 and a2 are both 0. So why is that the case here? I'm actually a little confused myself. So I took some linear combination of them equal to 0. We want to show that necessarily this and this scalar are both 0. We use the distributive property to distribute the addition here and the subtraction, and then we re-associated everything to write it as a real part and an imaginary part. Now this being equal to 0 means both the real part and the imaginary part are both 0 simultaneously. So now we know that so now we have a system of linear equations. A1 plus A2 is 0, and A1 minus A2 is 0, and we need this to be solved simultaneously. So the A1 and A2 needs to both add to 0, and the difference has to be 0. So what are the only two numbers that I can add together to get 0, and I can take their difference to also get 0? Anybody paying attention? So yeah, we basically boiled this down to two linear equations here. Yeah, 0 is the only solution, yeah. Sorry to burst everyone's bubble. How do we solve that? Well, I mean, A1 is equal to negative A2. You can plug in negative A2 here. You get negative 2A2 is 0. Divide by negative 2, you get A2 is 0. If A2 is 0, then A1 is 0 because their sum is 0. So, yeah. However you want to think about it, you can solve this linear equation simultaneously, and you show that A1 has to be equal to A2 has to be equal to 0. And that's what we wanted to show, because that says that the only linear combination of these two complex numbers where the coefficients are real numbers that give 0 is if both the scalars are 0. So that means that these two complex numbers are linearly independent as real vectors. So as a real vector space, the complex numbers are two-dimensional, but as a complex vector space, they're just one-dimensional. And that's a sort of obvious but very important statement, and something that could be very easily mixed up by newer students, undergrad students, or I mean, I've seen graduate students mess that up probably. I mean, it's kind of weird because you always think of dimension in the real case, right? So once you start dealing with dimension of complex vector spaces, it's just kind of a little bit weird. Like you have C3, which is a three-dimensional complex vector space, but it's six-dimensional as a real vector space, or six-dimensional as a manifold, six-dimensional as a topological space. Yeah, and I think, I don't know if Kyler's still here, but he was talking about Hodge theory, and I think, is it Hodge theory where they you have the like complex differential forms, and then you have the, all right, maybe I'm mixing up things. Yeah, I told you I don't know much about Hodge theory, but okay, so let's move on. Oh, wait, sorry, I didn't go over the second one. So let's show that they're not linearly independent as complex vectors. If we think of the complex numbers as a vector space over itself, okay, so this is part B. So we have the same vectors, complex numbers, which are themselves complex vectors now in the complex numbers space. So now we're going to let A1 and A2 be complex numbers. And assume A1 times 1 plus I plus A2 times 1 minus I is equal to 0. Well, actually, we can just show they're dependent just by picking some non-trivial linear combination, which is 0, and I'll just let A1 be 1 and A2 be I. Right, then if we have, 1 plus 1, or maybe I do need negative I, yeah. Negative I. This is negative I multiple of this, so it should be, that should be right? No, doing something wrong. Is it negative or positive? I think it's negative. 1 plus I can just check the first. Right. 1 times the first, so 1 plus I minus I, so I minus I is 0. Negative I times negative I is negative 1 plus 1 is 0. Right. Okay. Anybody have a problem with this? Complex numbers look like wedge products. What do you mean? Because I put the extra brackets? Wedge product. Oh, are you talking about Hodge theory again? I know Hodge theory, you have this wedge product thing, but yeah. I'm not going into wedge product at all. Yeah. No, I know, so am I. I'm okay with tangents. I mean, it's fine. Okay, so 19. Right. This is same section, I think. Yeah, 2A still. Okay, so this is problem 19. And I picked this problem on purpose because it doesn't. So the way Axler kind of proves things, right? He starts with a definition of finite dimensional, which says that it has some finite spanning set, right? So he's defining finite dimensional before he defines dimension. So it sounds a little weird, but I feel like he has his reasonings. So I'm not going to question it too much. But so for this problem, just because of the ordering of the way he proves things, it makes it a little weird. So I wanted to go through this problem and kind of explicitly write it out just in case anybody was confused. So we want to prove that the real vector space, meaning real numbers vector space, of all continuous functions on the interval 0, 1 is infinite dimensional. Okay, so it's a little bit funny of a statement, right? Because, I mean, I think in 2A he hasn't defined dimension yet, right? he defines finite dimensional and he says infinite dimensional is just not this. So, yeah, it makes it a little bit weird. One thing we know about finite dimensional vector spaces, though, is for sure he proves that every vector subspace or every linear subspace of a finite dimensional space is also finite dimensional. So we can use that statement. I'll kind of go over like why that's true a little bit, but we can use that statement, and then if we can come up with a subspace that is infinite dimensional, well, then we're done. Or equivalently, if we can find a list of vectors which is infinite dimensional, or sorry, if we can find increasingly larger sizes of lists that are all linearly independent vectors, and that list continues to grow forever with no bound, then you can prove that it's infinite dimensional. And so why is that the case? Well, he proves earlier that any spanning set is larger than any linearly independent set. So if you can find larger and larger linearly independent sets, well, the spanning set must be larger than that, and so there must be some there can't be any finite spanning set because there's infinitely large linearly independent sets, and the spanning sets have to be larger. So they just can't exist. There could be a spanning, well, there's always the spanning set, which is you just take all vectors, right? That's a spanning set. But I think you need to be a little careful because, for spanning lists, he's only defining lists for finite lists, so you can't really throw every possible vector in there. But there's always ways to extend these things to infinite stuff, so it's not really that big of a deal. But he wants to do it right? He wants to do linear algebra done right, so no hand wavy stuff, no, like this is just, basic reasoning. So, okay, yeah, so essentially the proof idea, I guess I'm not going to write it like perfectly formal, but I'll just write the idea here. And the idea is that every spanning set, spanning list, is longer than any linearly independent list. Comment, so is f times g defined as f composed g or defined as f of x times g of x, the product of the functions? Oh, good question. So there's no product defined here. We're not multiplying functions together, we're scaling them by real numbers. So when you say f times g, that's just not defined here. We're only defining if I take a scalar number, a real number, and I multiply it with a function. So really your formula should say something like r times f, where r is a real number and f is a continuous function. Then you have definition of scalar multiplication. You can add or subtract two continuous functions together, right? But we're not saying that we're multiplying functions here. Although you can multiply functions, right? And then that makes this an R algebra, which is an R vector space that has a multiplication where the multiplication is a bilinear map. So there is actually a multiplication in this situation, but we haven't mentioned that structure. So we're ignoring that structure here. We're just assuming that it doesn't exist for the sake of this problem, at least. Okay, so the idea of the proof, how to show that this is infinite dimensional. We use the fact, this is 2.25 in a previous section, I think, or maybe just earlier in the section, so 2.25. And that's what says every spanning list is larger than any linearly independent list. I think I went over this last time. I sort of hand waved the proof. I said you start with your linearly independent list, and you start adding vectors from the spanning list, and you're going to have to delete some vectors. How many vectors do you delete? Well, you're going to end up with some from the spanning list at the end, and you're still going to have your linearly independent list at the beginning, and you won't have deleted any of those because they're all linearly independent. You're only deleting dependent vectors. And so you can go through this argument. You can find it in the book. It's 2.25, but essentially he shows that if you have a linearly independent list and you have a spanning list, that the size of the spanning list is always larger than the linearly independent list. And that's kind of the crux of the argument here, because if we can find linearly independent lists that just keep growing in size, like I can find one that's a list of size 2, then of size 3, then of size 4, size 1,000,000. There's a size, quintillion vectors that are all linearly independent. I can just keep going on forever. Well, then the spanning list has to be larger than all of those, and there is no number larger than, if I can pick any number and find a linearly independent list that's larger than that number, well, then there can't be any finite number that contains a spanning list, because I can just add one more element and I can find a linearly independent list that's one larger than that. So that would contradict it being a spanning list by this statement. Okay. So what else do we need here? Now we have this fact, prove this fact, 2.25. And then what we can do is now we have to construct larger and larger lists of linearly independent vectors from this space. And if we can show that there is, if I can pick any large number n, and I can always find a linearly independent list of that size, and it doesn't matter what n is, no matter how big it is, well, then there can't be any spanning list, and then therefore it must be infinite dimensional. Because that's the definition of infinite dimensional. If there is no spanning list, then it's not finite dimensional, and it's, by definition, infinite dimensional. Okay, so let's just show, yeah, I guess we have to produce this increasingly larger and larger lists. But the book kind of gives you a hint, because continuous functions, that's what we're dealing with here, but the book talks about polynomial functions, and that's also infinite dimensional, and that's actually a subspace of this. So if you have an infinite dimensional subspace of another space, the larger space can't be finite dimensional. That sort of breaks your head, but it is true. Every subspace of a finite dimensional space is itself also finite dimensional. Okay, so our linearly independent list is going to be 1x squared x to the m. We'll call this, I'll call it big L M, list M. And this list is linearly independent. Why is that the case? So these are polynomials considered as functions on 0, 1. I should say that. But why is it obvious that they're linearly independent as real vectors? Right, polynomials form a vector space, right? Because I can take a polynomial, multiply by a scalar, real scalar, and I get another polynomial. But why are these independent? That's the question. I think there's not too many people left, so I'll start writing it out. But yeah, I mean, you take some linear combination, it's the 0 polynomial. So A1, I mean, it's kind of, every time you see prove this is linearly independent, you automatically want to think, okay, I'm taking a linear combination, it's 0, and now I want to show all the coefficients are 0. So A1 times 1 plus A2, or maybe I should, yeah, I'll write A0 for the degree. A1 times x plus A2 times x squared, AMX to the m equals the 0 polynomial. Well, I mean, like, it literally can't be the 0 polynomial unless all of these are 0, right? Because the 0 polynomial has no x's. If any of these are non-zero, then we have some x. So I'll just say they're all 0 by degrees. Equals 0 by checking degrees. Right? If any of these is non-zero, we just have some non-trivial polynomial that's not 0, right? So, yeah. Just look at all the monomials, check the degree of all of them. This has no monomials. If I have anything here non-zero, then the degree is not negative infinity. It's whatever the highest non-zero coefficient is, right? So that's one way to think about it. You can just compare the degrees, 0 polynomial versus these, and then, yeah, by necessity, all of the coefficients have to be 0, or else you'll have the degrees won't match, right? Yeah. If you have two equal polynomials, they have to have the same degree, right? Or else, I don't know what degree would mean if the polynomial could have 2 different degrees for the same polynomial. Any questions? Yeah, yeah. Push that Discord. All right, I think this is the last problem then, and I really do like this last problem. So here we're looking at a particular subspace of polynomials. We were just talking about the polynomial vector space, how polynomials themselves are a vector space over the real numbers, or if they're complex polynomials, they could be complex vectors as well. But so this problem, this is in 2C, section 2C. So the last section on finite dimensional vector spaces. Why do the functions have to be continuous? What do you mean have to be? I mean, that's just what the problem asked us. I think I get what you're saying. Yeah, I mean, the functions have to be continuous. Well, it's not that they have to be continuous. It's that if they are continuous, then they form a vector space because the linear combination of continuous functions is also continuous. A priori, maybe it's possible that the linear combination of continuous functions becomes discontinuous, right? You would have to prove that it's necessarily true that if you start out with continuous functions, you take a linear combination, they stay continuous. Otherwise, it's not a vector space. But you could, I think I get what you're saying though. You could just take all functions on 0, 1, and that would also form a vector space. You're correct. So it doesn't have to be continuous in the sense that there's nothing forcing us to take only continuous functions. We still get a vector space if we take all functions. But if you take continuous functions, that's a subspace. So actually, yeah, you could show that the subspace of continuous functions on 0, 1 is actually a sub-vector space of the full vector space of all functions on 0, 1, where they don't have to be continuous. They could be discontinuous everywhere. They could just take on arbitrary values at any point. If you take any of those functions, you can still add them pointwise, and you can still scale or multiply them, and they're still functions. So yeah, they don't have to be continuous, but if you do take continuous functions and you scale or multiply them and you add them together, they stay continuous, and that's why it forms a subspace. Okay, this is 2C. What are we doing on time? Okay, yeah, pretty much good. Okay, so 2C, section 2C, problem 3, part A. They give us a set of polynomials, and we want to find a basis. So we have U, which is all polynomials, where if I plug in 6 into the polynomial, I get 0. So it's all P in P4 of F, such that, that's my little semicolon, P of 6 is equal to 0. And we want to find a basis for this subspace. For U. Okay. So what kind of intuition should we have for this problem? Maybe offendum. Maybe you might want to think about this. So if I have a polynomial and I plug 6 in and I get 0, what types of polynomials have that property? I guess that's kind of what we're trying to figure out. And we also need to pick these polynomials such that any linear combination of them also, P of 6 is also 0. Does anybody know about zeros of a polynomial over a field? Like If I know that there's a 0 of a polynomial, what can I do? Yes, perfect. Yeah. Very good. Yeah. Yeah, so what allows us to do that, Effendum, though? So you're perfectly correct. We can express the polynomial as x minus 6 times some other polynomial. But what is the process, or what is the theorem or idea that allows us to say that? So let me just write down what you said. So if p of 6 equals 0, then that implies that x minus 6 as a polynomial divides p. In other words, p of x can be written as x minus 6 times q of x for some q of x. So yeah, what statement or theorem? I don't think it's in this book, so I'm not like calling anybody out or anything. If you don't know this, that's totally fine. Especially if you read the book and you're saying I never read this anywhere. Well, this is probably in like Dummett and Foote. If you remember, I was talking about abstract algebra books. You have the Jacobson book. You have Dummett and Foote, which is like a little bit more advanced. In there, they'll talk about polynomial rings over a field, and there's a theorem that says that essentially, like, if you have a number that you can plug into the polynomial and it's 0, yeah, you can divide out by x minus that number. So essentially, the theorem, it's long division, right? I mean, it's the same long division you do for like numbers, but now your polynomials are the ring and you're dividing out by polynomials. So essentially, q is like the, right? We're basically saying like x minus 6 is p divided by q. And there's no remainder, because if there was a remainder, it would have degree less than x minus 6. So the remainder has to be 0. Otherwise, p of 6 would not be 0. So we have no remainder here. We just have pure division, right? We can divide p by x minus 6 and we get q. Right, so essentially, and now we can do the same thing for q. So now either it's the case that q of 6 is 0 or it's not. If q of 6 is 0, we can factor out an x minus 6. And we can keep factoring out x minus 6's until maybe the polynomial is just x minus 6 to the 4th, right? Because we have polynomials of degree 4 or less. So the polynomial could just be x minus 6 to the 4th. But, yeah, those are basically all the cases. Either x minus 6, you divide out by it, and q now is not a root, or it still is, and we can keep factoring x minus 6 out. So essentially, you need to do a little bit of work here. This is definitely not a full proof, but here we can say that a basis for u is the span of x minus 6, x minus 6 squared, x minus 6 cubed, and x minus 6 to the 4th. And now we have a list of 4 vectors that's linearly independent. Again, you have to show that these are linearly independent, though. So you have to take some real linear combination of these, or actually we're over some arbitrary field. So you have to take some linear combination of these, set it equal to 0, and then you have to show that each of those coefficients is 0. Is that obvious? Why that's true? I'm actually not even sure if that's obvious. I don't think I did it out. Yeah, I didn't do it out. Hello, mouse. Hey, e to the 2 pi I. 2i. I always want to say 2 pi I instead of 2i pi. I don't know why. Yeah. So yeah, I'm just trying to think if this is obvious or not. I didn't write it out on my notes, which of course, the one thing I don't write out, it's the hardest thing to prove, of course. So has anybody thought about this at all? Is this obvious to prove? So is this list linearly independent as polynomials? As like thinking of the polynomials as vectors. They're vectors in the sense that we can scale a polynomial and I get another polynomial. I can add two polynomials together, I get another polynomial. Right? So essentially we would have to write out something like, some scalar times x minus 6 plus some scalar times x minus 6 squared plus some scalar times x minus 6 cubed plus some scalar times x minus 6 to the fourth equals 0, the zero polynomial. And then we would have to show all the coefficients are 0. So why is that true? I feel like it's obvious. Maybe we should write it out. So it's definitely a spanning set because you can just keep dividing out by x minus 6. So you can show that, you can show that if p of 6 is 0, that it has to be some linear combination of these. There's no other option. But here, how to show that it's linearly independent. Oops, maybe I shouldn't have erased it. Or yeah, I'll leave it at the bottom. Or no, we can rewrite it. It's not a big deal. Short answer is upper unitriangular matrices are invertible, but at this point in the book you probably have to translate that to remove the matrices. Right, yeah. Yeah, I think that's going to be proven later. I think he's going to, instead of dealing with upper triangular matrices, he's going to talk about a basis of generalized eigenvectors. So you have, it's essentially the basis that you would pick that in that basis the matrices would be upper triangular. But what was I talking about again? Oh, right, to show that this is linearly independent. Wait, so essentially, Stuckey, are we just, this would be like a translation into, I know, well, I guess we can't really do that though, because he doesn't do that yet in the book. So even if we don't talk about matrices, I still don't think we could use that argument. Not that that wouldn't work, just that I don't think he's gone enough into that. The scalars must be equal to 0 because otherwise we would not have a constant polynomial. Well, you don't know that, right? I mean, actually, okay, yeah, you can go one at a time, right? So we can start at the largest degree polynomial. Right. Okay, I see it. So if a1 times x minus 6 plus a2 x minus 6 squared plus a3 x minus 6 cubed plus a to the fourth x minus 6 to the fourth equals 0. It's because they're decreasing degree. So there's an x to the fourth here, and this is the only one with x to the fourth. And so that means that a4 has to be 0 because there's a 0 over here. So it's kind of like you go one at a time. So first, a4 is 0 because that's the only term that has a x to the fourth. And then since a4 is 0, I can just ignore this term, right? And then that means that this is the only term with an x to the 3. And then so that means that a3 has to be 0 also. And so on. So all the a's are 0, basically. Yeah, so I think this whole deal with the upper triangular stuff probably is overkill for this. And I think that's actually kind of Axler's, that's kind of his whole theme of this whole book, which is like, you have this whole story of matrices, determinant, eigenvalues, upper triangular matrices, and all this stuff. but he kind of avoids all of that and puts it all at the end of the book. So he does everything theoretical that he can possibly do, and then he says at the end, okay, if you fix a basis, then you get these coordinate vectors, then you get matrices, and now let's prove everything about determinants and everything. But he basically avoids all of that. I don't know. He sees it as unnecessary for understanding it, I guess, and I can sort of see his point, but I do sort of push back a little bit because I think doing the calculations, calculating determinant, I think that is important for students, so I don't think it should be completely avoided. And he doesn't completely avoid it, he just puts it at the end, so I don't know. Guess it's all opinion, preference, learning style. This is definitely less applied. I mean, obviously you can see we're doing not so much calculations, but I would like to, we will get to the calculations. I think next Wednesday I'll do more kind of calculation type problems. Okay, so let me just finish this problem real quick. So we showed that it's linearly independent. I didn't really prove that it's a spanning set, but I gave you kind of like an overview of why you might believe it because of this division algorithm. And then for part B, they want us to extend this to a basis for all polynomials. And so what vector can I add to this list? Well, if you think about it, this is the space of all polynomials that when I plug in 6, I get 0. So all I need is a polynomial that's not 0 when I plug in 6. So can anybody give me a polynomial that doesn't have 6 as a root? And it has to be, well, yeah. Oh, yeah, I guess technically, yeah, it can be any polynomial that doesn't have 6 as a root, yeah. I guess there's just way too many. That's what always happens. Like if you ask a math class full of students for a question, but it just has like way too many answers, then you just never get a single answer. But yeah, I mean the easiest answer is just 1, right? But yeah, you could pick really any polynomial that doesn't have a root of 6. So part B here. They want us to extend this list to a basis, and if it's not 6, it's 7, right? Yeah, exactly. Right, actually, yeah, we'll add 6 to the basis, right? So here, if we want to extend the basis, let's say it's the span of x minus 6, x minus 6 squared, x minus 6 cubed, x minus 6 to the 4th, and then we're going to throw in I'll throw in a 6, but not a 7. I am having an effect. All right, yeah, so any polynomial that when we plug in 6, we don't get 0, there's a constant polynomial. So yeah, any constant polynomial works. Any polynomial that's just not equal to 0 when we plug in 6 also works. Yes, I do need a larger word, but I know. This is top priority. I know. Okay, so now we extended the list. We had these 4 vectors. We added a 6. Not a 6th vector. We added a 5th vector that happens to be 6. And now this will be a full basis because we know this is 5-dimensional. We know that these are linearly independent. We found a vector that wasn't in the span. So we know that this bigger list is still linearly independent. Otherwise 6 would be in the span of these, but it's not. And now the last part says, okay, now we want to write P4 as a direct sum of U, which was spanned by these 4 vectors, and some other space. And the other space is just going to be the span of the vector we added. New to the maths community on Twitch, or am I not paying? Yeah, I'm pretty new, yeah. I think I've been doing this for like a month or so, maybe a month and a half. Yeah, actually, it's only been a month. Oh, no, 2 months. Yeah, 2 months. Despite the feeling and dust on the chalkboard, but Zach seems to live and breathe it. Yeah, I mean, I'm honestly, I kind of piss people off because I don't really hate either. I can use chalk and I can use whiteboard. Not a big deal to me. His lungs scream for death. Whiteboard over chalkboard. Feels amazing, man. Thanks for sharing your expertise with this. No problem, yeah. No, I love teaching math. Especially linear algebra, group theory, all this abstract algebra stuff. I will have to go into some calculus every now and a while because everyone loves their calculus. Tinker, come to Discord. You can be converted. Okay. So I think that's basically it. So then the last part, C. So we're just looking at these 4 vectors here. And then we extended the basis to a basis of the full space by adding, I guess I'll use green here, this last vector. And the last statement, part C, says now we want to write this as a direct sum, and it's going to be a direct sum of the span of the first 4 vectors, which is u, direct sum with the span of the last vector. And this is very similar to my notes say to look at part 2.33. And 2.33 describes how you can do this extension of basis to get this direct sum, this u plus w. But here our u is the span of these, and our w is the span of the vector that we added to the base to get a basis. So let me just write that. Yeah, all right. Since I'm getting so many complaints about the board, so I guess I'll probably have to get a bigger board for next week. So maybe not by Friday, but probably by next week I'll have a bigger board. Okay, and then just to finish up what we had. So now, yeah, span of these is u, and we can write now P4 of f is a direct sum of u, direct sum of w, where w is the span of the polynomial 6. Or I guess it could be 6, 7. 67. But yeah, you can just pick any non-zero number there. It doesn't really matter. It can be any constant polynomial. Let's just leave it at 6. Just I don't want to go too crazy on the memes. So we have 4-dimensional space here, spanned by 4 linearly independent vectors, and then we have a 1-dimensional space here. It's spanned by just this one vector polynomial. And sometimes it's good at the end of a problem, make sure everything matches up. So with the dimension, and we know that the dimensions should add with the direct sum. So this is a 5-dimensional space, and it's a direct sum of a 4-dimensional space with a 1-dimensional space. So 4 plus 1 is 5. Dimensions make sense. Everything's good. Okay. 5% of the goal. Oh, wow. Thank you. Thank you. Somebody tipped. First tipper. Yeah, so we have this Ko-Fi link down there. Oh, I can't point. Everything's backwards. And, you obviously don't have to donate anything, but if you do want me to go over something in particular and I'm ignoring you, or you just really, really want me to go over it, and it's something that, I didn't have enough time for or something, you can always send a tip, some sort of reasonable amount for how long the problem is going to take. If it's going to take me like a whole day to do the problem and go over it, then probably like $5 or $10 is not enough, but, just be reasonable, of course, and yeah. Tinker. So wait, who's Tinker? Is Tinker high potential? Oh no, Tinker is a different. Okay. Interesting. Okay, thank you guys very much. I really appreciate the tip. Yeah, it's my first one. I really want to keep doing this. I really enjoy doing this. As someone with too much monitor and whiteboard, I'm pitching to get bro set up better. Yeah, no, I will get a better whiteboard. You don't have to tip for that. I'll just get a better whiteboard. You can tip anyways, but all right, I'm gonna end it here, guys and gals.